Okay, folks, we are back. And this one's going to be a little quick from a recording standpoint, because what we're going to do, also because the battery's getting a little low, but that's okay, I can redo this one if I need to. So we want to review the electromagnetic spectrum and some mathematics that go along with that as it relates to the environment. So we're going to do this pretty quickly, and I'm going to set up some math. If I was teaching this as a regular class, I would sit there and stare at you and give you time to solve the math. I don't have to do that on a video. So what I'm going to do is set up the math and then ask you to stop the video or keep watching it. And I'm just going to set up the math and give you answers, but then it'll be up to you to go back and figure out how to do those and then to go do the homework problems. Okay, so we don't have a ton of time here with this one, so I think this will be a good quick one, and let's get going. So the OpenStack section, if you need a refresher on the electromagnetic spectrum, is 6.1. There's that graphic on the slides that gives you, it's a really busy graphic, so there's no point in me talking about it, that shows you wavelength and frequency and how those are related, how different wavelengths and frequency manifest themselves in nature and other processes. It's a busy graphic, but it does the job. Okay, so let's cut to the chase here. So one measure of electromagnetic wave is the wavelength, literally how long a wave is. I'm not going through all of that now. And we typically will measure that in nanometers for this particular course, in this particular domain. So down in the low wavelength, high frequency region, we have, we're down in the region of X-rays. Then you get up to about 250, 350, 450. Again, these borders are fuzzy. This is where you get ultraviolet, and it goes from C to B to A. The shorter the wavelength, the higher the frequency, the more dangerous, if you will, to biological life. And then you get into 450, 550, 650, 750. That's your visible region of the spectrum, Roy G. Biv, but this goes reverse. So it's V, I, B, G, Y, O, R. I didn't really get that scaled properly, but that's the visible region of the spectrum, important to us. And then when you go beyond the red, that's when you get into the infrared, an important region of the spectrum, especially when it comes to climate change and global warming. Okay, let's do the math. So that was number one on the slides. Number two is electromagnetic EM mathematics, so that's fine. So here's some equations. The energy of one photon of light, one photon, is a constant called Planck's constant, and this is the per photon energy. We don't want to know for one photon. We want to know about a mole of photons. So we're going to have to scale this up with Avogadro's number, 6.022 times 10 to the 23rd. So this is going to be measured in joules. That's just the equivalent, the triple, not equal, but equivalent of joules or units. This is called Planck's constant. I'm not going to write that, but it's 6.626 times 10 to the minus 34th joules times seconds. You don't have to memorize that. If you want to write that on your periodic table, that's fine, or just have it handy. And this is times not the wavelength, but the frequency, which has units of inverse second. It's how many times the wave goes up and down per second, which some books will still call that a hertz. Fine. So that's mathematical equation number one. The second equation that's useful is if you take the wavelength of light times its corresponding frequency, you get a constant called the speed of light, which is 2.998 times 10 to the 8th meters per second. So that indicates that you have to put in your wavelength in meters, that's fine, nanos 10 to the minus 9th. So you don't put it in nanometers, you put it in meters, that's no problem. And then frequency, you just use inverse seconds. That's equation number two. And then if you actually combine these two equations, you can get energy equals hc over lambda. And that's equation Number 3, it's really not a new equation, it's just a combination of 1 and 2. And it's also useful to remember Avogadro's number given the symbol capital N. 6.022 times 10 to the 23rd. Why am I looking at this? Now that's Avogadro's number. What does that mean here? That means photons per mole. So a mole of photons is 6.022 times 10 to the 23rd photons. You probably just used that number, but not for photons before. Okay, let's do the problem. So the first problem, I'm going to try to fit these in over here, and I'm going to set these up and give you the answers, but if you want to stop the video and do the 2 example problems on the slides. So the spectroscopy of ozone and the spectroscopy of atomic oxygen production. So if you just want to stop the video and try doing these yourself, that's fine. So this is example 1. And it doesn't really matter what we're doing, but we're trying to do this usefully here. So this is the spectroscopy of ozone. So I think it says, you go back to that spectrum and figure out what is the wavelength most efficiently. Okay, well you go back to that graph that shows the absorption spectrum, and this is number 1. And again, stop the video and do this on your own. I came up with a wavelength of maximum absorption of around 255 nanometers. And that corresponds to the ultraviolet region C. So it's really good at absorbing UVC, which is good. And then the question says, what are we doing? Calculate the energy of a mole of photons. This is where I'm just going to write this out, and you can do it on your own. Just make sure you put in your wavelength in meters. So I'll let you figure this out, but it's 2.55 times 10 to the minus 7th meters written in proper scientific notation. So the equation gives you 7.79 times 10 to the minus 19th joules per photon. Then what we're going to do is convert that to kilojoules. So 1,000 joules is 1 kilojoule. And it may be tough to read here, but a mole of photons is 6.022 times 10 to the 23rd photons. So now we have to do the formula and then a couple of unit conversions, and then you'll end up getting 469 kilojoules per mole. Okay, so we're just doing the math. Just get the math right. I'm not worried about what it means right now. Okay, that was example number 1. Example number 2, what are we doing there? Use either the enthalpy of photolysis or the bond energy. So it's the reverse equation. So we're using an energy and going backwards to wavelength. No problem. I just need some space. So do that one on your own. You don't need me. Okay, what's the answer? I'll just give you the answer. I came up with 240 nanometers. So if you want to just do the math, it's 240 nanometers. So example 2, I'm going to use the enthalpy of positive 498.4 kilojoules per mole. need the energy in joules per photon. So I have to go backwards here. So this is 498 kilojoules per mole of photons. So it's kind of like reverse. So we know a kilojoule is 1,000 joules, and we know a mole of photons is 6.022 times 10 to the 23rd photons. So the bottom line is, when you do the conversion, you should get a really small number. And I get 8 point, I'm carrying extra sig figs, I don't know why. There should really only be 2, oh, this was 48.4. No, I have the sig figs right. So I got 8.276 times 10 to the minus 19th joules per photon. Because it's really small, because it's 1 photon. And then I'm going to take that third equation, and we're trying to solve for wavelength. So if you solve that equation, you're going to get hc over E. And I'm not sure you need me to do this. So I can probably just talk you through this. So you put Planck's constant here, you put the speed of light here, you put the energy here, which we just brought down, and you follow your units, you end up getting 2.400 times 10 to the minus 7th meters. And if you need to see it, go back and review your Greek prefixes. 1 nanometer is 10 to the minus 9th meters. And you come up with 240.0 nanometers. And I think the problem says to, what is it? Confirm that this wavelength lies in the UVC region, which it does. Okay, so that's the mathematics of the electromagnetic spectrum. I think there's a couple of homework problems on that, but the book also has some more problems on that. So those are the kinds of things you're going to want to be able to do. Going from energies to wavelength, wavelength to energies, frequencies, all that stuff. So make sure that you review that, and that'll give you a good start also with section 6.1. Okay, good work.